All right. So the last portion that I would like to discuss, and I think this is a good place to stop. Otherwise, then it seems like it's sort of like hanging at the capacitor, and it seems like, as I said, it's supposed to. I mean, on originally it was planned that the plan was like try to finish up this lecture on Saturday morning, so like easy going, and then we missed that Monday's class, so that's why. Okay, so let's dive into it, and it's just like a tiny bit now. There will be no more calculus. That's sort of like a cool down process right here, so we don't have any like crazy dot products, integral, Gauss's law or anything anymore. So what I would like to go through is just showing you what can be modified that capacitor to make it sort of like, okay, more useful, plus enhance the capacitance by not changing the shape of the capacitor. So we're going to put something that we named dielectric material in between the space that was blank before. So now we're going to fill up that with the dielectric material, and then we'll see what happens to it. And once we have that, then I'm just going to sort of briefly talk about Ohm's law again. We have done this. I think you guys have done this many times. V equal to IR, or you might be remembering in terms of I equal to V over R. But that's not the point that I would like to do today. You guys sort of familiar with the concepts of the current. You're familiar with the concept of the potential difference already. So the final, sort of like the finale of this whole thing is the Kashaf Rule. This is the one I want you to get. I mean, some of you in this class probably have done this already, especially for those that may be doing electronics and other stuff, or you forgot the electric law. Okay, so don't worry, it's simple enough. It's only like a single law that you need. All right, so and there's no calculus and everything, so it should be good. Okay, all right, so that's all I want. So let me finish up about the dielectric in the capacitor first, and then we'll briefly review about Ohm's law, and then we dive into Kashaf's rule, which is very easy to use. And the thing is, I mean, to me, it seems like it's useful to know. And at the end of this lecture, all I'm asking is just like, how can we solve this kind of circuit? Which is, I think, is more realistic. All right, we're not going to just using Ohm's law all over the time, every time. So we're going to have some circuits that look more complicated. And what kind of Kashaf's rule will allow us to be able to solve this kind of circuits? And that's it. That will complete the whole thing. So we probably don't want to have to go through the RC circuit in terms of the analysis. But I hope I will sort of like give you an example, and then you will be able to answer without, I mean, you don't even have to use Kashaf's rule to answer the question. Okay, sounds good? All right, so let's start with the simple thing first. What kind of material that I squeeze in between the conducting plates and allow you to adjust some value of the C? It turns out that material, if you take the material to be a dielectric material, then what it can do is this. When you say the dielectric material, if you're sort of familiar with the polar molecule in chemistry, maybe like H2O, water, you guys sort of remember vaguely that even though the H2O molecules are neutral, but when you sort of like dive into a single molecule of this one, the electrons seem to spend more time around oxygen molecules or oxygen atoms than the hydrogen atoms. This is, I mean, they explain it in terms of the electronegativity in sort of like the periodic tables. All right, so that means if you sort of like consider this whole thing as like a piece of molecule, so you can pretty much identify that the upper corner seems to be a little bit more negative than the bottom one. So you might be able to sort of think of this one simply, just model this one like a capsule, something like that. One side of it is being positive and the other side is being negative. So if you imagine this, so that's where the figure is showing. So it has some sort of like a polarity. And then you can maybe sort of identify this by having some like a mini arrow showing like there is a direction of the polarity inside each molecule, something like that. And then you can define this as a vector pointing from negative to positive, and it doesn't matter. But then the thing is, you can imagine this arrow to act like a compass. But the compass interact with the magnetic field. Here, or it's charged. So one positive, one negative. So it will interact with the external electric field, guys. That's it. In the same manner, in the sense that, of course, positive charge try to flow, go along with the field. The negative one try to go against it. But of course, I mean, you cannot just push them apart. So the best thing that you can do is, of course, you're going to rotate. Okay. And at the end, the final result that you are getting is just the orientation of those molecules in the direction of the external field. Does that sound sort of reasonable? Yeah. So the idea is just like you're having a compass, but now it's the electric compass. So when you apply external force, those molecules will rearrange itself to make the orientation of the molecule's polarity to be in the same direction as the external electric field direction. Perfect. That's kind of cool. So with that, then by having this squeeze in between, so you do something else to the internal portion of this space. And let's see how it's done. The effect of having the dielectric molecule in between is this. So when those molecules are lined up, so this is a cartoon version of that. So remember that these molecules will be huge, like you have billion of molecules, right? So when you look at the positive ends of this one, it will always have some negative neighbor. So somehow its friend will have like a negative value, I mean, negative charge. So when you look to the other side of the molecule, it will be somehow near to the negative side of the other molecule, the nearby neighboring molecules. So overall, as long as you stay inside the material, every time that you are looking at the positive area of the molecule, you will always be sort of next to the negative area of the neighboring atoms all the time because of the lining up of these molecules. However, if you look here, there will be the one on the left ends of this one, which is, think of it like on the surface of the dielectric material. It doesn't have any neighboring positive molecules to cancel with. Does that make sense to you? Same thing with the right ends of this one. It seems like there's no neighboring negative molecules to cancel its charge with. So that means the surface of the dielectric material will behave like there is going to be like a left surface charge, I mean, left negative surface charge on the dielectric material. And on the right, you build up like a positive surface charge. Yeah. So by having this, it's like you induce the internal capacitor. Think of it that way. You have an external plate, right? You have two plates outside generating the electric field. Once you squeeze in the dielectric material, it turns out the dielectric material itself do the same sort of idea, like you generate a parallel plate capacitor somehow, but it's in the opposite direction. Can you see that? The electric field that get induced inside the dielectric material point in the opposite direction to the external field. That's a problem. The problem in the sense that, so the net effect is you get some cancellation. Okay, maybe I just drew this one too big. I don't want it to have an impression that you're going to cancel everything. But anyway, all right, you generate something like that. Okay, so there is an induced electric field. Let me put it in like an E prime. So at the end, the net electric field that's left over from this cancellation is going to be smaller. See? Tiny. Okay. So what happens next then? It turns out, okay, let me write this one. Okay, don't worry about this Gauss's law or anything yet. But the idea is the voltage difference, you remember in the case of the simple electric field that is uniform, is just E times D, correct? Yeah, we did that in the previous lecture. Then what you have right here is you reduce the E because of that cancellation. So that leads to the lower value of the potential difference across the plates as well. Whoa, that is kind of nice. So by having that, go back to the definition of the capacitance is just the charge per voltage difference across the plates. So what you get here, guys, can you see now? Of course, you make this value smaller. At the end, you are making the C bigger.
Okay.
That's it. So this is the reason why by introducing dielectric material in between the space, you enhance, you improve, or you increase the value of the capacitance of the capacitor by not changing the area surface. You're not changing the distance between the plates. You only squeeze in the dielectric material to it. All right. And it serves an extra purpose of the question that it's been asked before, which is like, hey, if you have just like a blank space, so you have a chance that these two plates will just touch and then just, short circuit charge with discharge and everything, and you don't get anything out of it. So by having dielectric material in between, yeah, at least you have some support. I mean, sort of like, okay, that's good. They're never going to touch. And then plus you enhance the value of the capacitance along with it. Okay, sounds good. All right, this is nice. Okay, but how much, John? How much can it increase? So to make this sort of like easy for everyone, I don't know intentional or not, but it makes sense. You have a value that defines the ability of these dielectric molecules to line up in the external field. And we name it the K. And it's called dielectric constant. Yeah, that's nice. So that means every time you talk about a dielectric material, then you can ask for the dielectric constant value of that. But what does that do? It turns out this dielectric constant is just a number, which is good, right? No units or anything, it's just a number. But what does that number do? It turns out, come back to this, guys. Remember this epsilon naught that we had before in the Gauss's law? There is a naught. That naught has a meaning. This means vacuum, blank. So imagine this. If you put a charge, just like what we did before, and everyone knows that, okay, if you have a charge, positive charge, this charge will generate electric field all over the place, like this, right? Okay. And I think this is going to be easy to conclude. And you say the electric field over here is just going to be 1 over 4 pi epsilon naught, that's the K, times the charge Q divided by the separation or the distance R squared, right? That's done. Here comes the question. Well, hey guys, what if I place this charge in water? Oh, water is supposed to be blue, I guess. If I place this charge in water, what will happen? No, about that, it's supposed to happen the same, except the surrounding has already changed from the vacuum into water. The way that you can manipulate this equation is just simply, here we go, guys. Look here. That's it. I don't know. Did you see it? All right, let me do it again. What I did was just bam. So what I'm doing is just I replace the vacuum with water. So what I'm thinking of doing is just like, hey, can we figure out what should be the permittivity of water? That's it, guys. Simple. And what is it? It turns out if you look at the dielectric constant of water, let's say like, okay, that's around 80, let's say. So it turns out this epsilon of water is just going to be that dielectric constant multiplied by the epsilon naught, and that is it.
Okay.
I hope this give you like a very good relationship between what's going on when you change the medium that the charge is located. So you just change the epsilon naught into epsilon of that material. And if that material is a dielectric material, you have a constant that's named dielectric constant that you know exactly that this is a factor that go in front of the epsilon naught, and then you're done. Okay, so that's a good thing about the whole business that we are doing over here. Remember the formula for the capacitor, the capacitance that is, okay, let me write it down. I think, okay, for the capacitor, parallel plate is an epsilon naught A over D, right? This is the one that has a vacuum in between. But now once I squeeze in the dielectric constant, what I'm doing, just multiply by the dielectric constant and I'm done. That's it, guys.
Okay.
Okay. Or actually you can re-express this one as an epsilon A over D, where the epsilon is a permittivity of the material that you have in between. But it's just so simple that it's just a dielectric constant. Okay. I'm using K over here, even though, well, in the textbook and some of the textbook, they use like kappa, but in writing, I don't know, K seems to be easy to write. But I mean, you can use kappa and everything as well. It's the same thing, right? But I'm afraid that there are too many Greeks, I don't know, terms in the formula. All right. So let's take a look at some common, I mean, you will be surprised that paper itself also have some dielectric constants that is pretty good. So that means if you have a parallel plate and then you squeeze in paper, you already enhance it by 3.5 times. Okay. And I think what people are using right now, like here, see, this is a ceramic that I was talking about. So that means if you have a solid state capacitor and then you use, I mean, you can use ceramic here. So you can enhance like, 100 times. So that means you can still having a very high capacitance by not, I mean, by keeping the size of the capacitor pretty small. So this is very neat. All right. And then you avoid oozing out all the liquid stuff. So back in the day, I think they used some liquid solution or something like that. So over time, eventually it's gonna, expire. It's gonna get bad, and then coming out of it, and then your electric board will be pretty much trashed, and then you have to replace the capacitor. That's what it is. Okay, cool, guys. So I hope this one works. So I'm just showing you, don't worry too much about this one because we say we're not going to try to do cylindrical shape capacitor, but I'm just want to show you that how simple it is. If you have a formula for the capacitance in just a regular case that you have space in between, if you want to change the space in between into something else, you just multiply by the K, the dielectric constant, and then you're done. And that is it. Okay, so first part is kind of easy to take. So let's take a look at some exercises over here and see how it goes. You have a parallel plate air filled. So let's assume it's just air, so it's blank. Has a capacitance of 50 picofarads. So this is pretty small, even though you sound like, okay, that is pico. Pico is 10 to the negative 12, but it turns out 1 farad is huge. Okay, so in general, when you have like just like a circuit board in your computer and other stuff, you are dealing with like a microfarad, nanofarad, and stuff like that. So picofarad is not bad. It's just normal for small circuits. Okay. So if each of its plates has an area given, what is the separation? So part A is simply just plug and play. So you say for a parallel plate capacitor, so let me emphasize it to be just a parallel plate, it's just an epsilon naught A over D. So all you need to just plug in. So D is going to be epsilon naught, a constant, A is given, and C is also given, and then you're done. Okay, just put the SI system in there. And then 50 times 10 to the negative 12. Done. There you go. All right, and the final answer will be in meter. What is titanate? Oh, I guess it's gonna be like a titanium mixture ceramic, I think, because of the name. So like strontium titanate. So it's gonna be mixture between strontium and titanium, I think. And then you do it in terms of like, there must be some chemical name for it. Just Google it, I guess. I'm not so sure. I'm guessing, but it sounds like that. Okay. All right. Part B. So if the region between the plates is now filled with material having the dielectric constant 5.6, what is the capacitance? Is that cool? Oh, Dan, are you serious? Well, yeah, I am serious. So let me put like a C prime then. You already filled the space with the material, the dielectric material. So it's going to be just that. I mean, you can use kappa, okay, of that C original, and you're done. That's it. So it's going to hit enhance 5.6 times of that 50 picofarads. Simple as that.
Okay.
See, isn't that nice? I think it's nice. So try again. You have an air-filled parallel plate capacitor with a capacitance of 1.3 picofarad. The separation of the plates is doubled, and the wax is, there's wax is inserted between them. It turns out the new capacitance is 2.6, so you double the capacitance. What is the dielectric constant of that wax that you just put in? Oh, yeah, this is not bad either. So let me do like a parallel plate. Just a regular plate is going to be epsilon naught A over D. So because this is a comparison between two setup, what I can do is just like put a C parallel prime in it. That's after squeezing the wax. So the wax, if it has a dielectric constant of K, the capacitance will be K epsilon naught A over D. You guys with me? Okay.
Okay.
And now all I need to do is just compare them. I just take the ratio between the two. All right. So let me put sort of like everything in full detail over here. Because you are not changing anything except you double the plate. So let me prime that A too, because you're changing the A. However, the distance between the plate, you are not changing. And then so I'm just keep D to be exactly the same on both cases. Sounds like a plan? All right. So with that, epsilon naught is gone. The D will disappear. So the A is doubled. So that means on the right side of this one will look like a K times 2. It's just a ratio. Okay. Oh, wait. I'm sorry. I got it wrong. It's a separation that is double. My bad. Sorry, guys. Ooh, not the plate area. My bad. Okay. So what I'm going to do is I'm going to prime that D there. So distinguish between the two cases. Sorry, guys. So it's going to be D prime right there. And A is being kept the same because you are not changing the size of the plates. So I cancel the epsilon naught, I cancel the A. So what I'm getting is going to be K. All right, over here, you're going to get, okay, let me flip it up and down again, D over D prime. There you go. So on the left-hand side, the new capacitance is 2 times, it's twice as big. So this is 2. And the D prime is twice the D, so you get 1/2 over here. And that's it, guys. So the dielectric constant that you are using is 4. Done. Okay. All right. So I hope this is sort of like okay enough for you to be able to just, okay, at least now we know the actual stuff that is going on with it. Okay. And this one, even though it's a coax cable and everything, so this one, don't worry about it because we are not, as I said, we are not trying to use any cylindrical shape of it. However, if you really want to do it, and now I hope you understand it, all you need to do is just take the formula and then just apply it. Okay. And all the parameter, if you notice, the parameter that determine the capacitance of a capacitor depends on the physical stuff here. How long is it? What is the outside radius, inside radius? What kind of material you are using? Done. Okay, so I hope you see the common characteristics of all capacitors. All right, it depends on the physical parameters of the capacitance of the capacitor that determines the capacitance of that capacitor. Whew. It's a long word there. All right. Okay, so we only care about the spherical shape, let's say. All right, so I don't want you to worry too much about the cylindrical shape, but the underlying principle are the same. Okay, so I think the reason that I cannot, I mean, actually I can stop here for the final, but I think it will be nice to be able to just, just squeeze in this one stuff that gonna make things that you learn a little bit useful and then give like a grand conclusion to the course. Because you have to charge the capacitor. So if you're not talking about the current, that would be kind of like illegal somehow, because I mean, what we have been doing so far was like electrostatic. Everything is like static, no movement. But it's unfair for you to be able to charge a capacitor and not talking about something flow into the capacitor. So that's why I have to introduce currents, because I am going to, parade all those charge into the capacitor. So it's supposed to have some flow in it. So go back to the definition of the current. It's a simple one because it's the same as any current. You learned fluid dynamics before. The current flow of water is going to be the volume of the water per unit time, right? Now, what we would like to look at is the electric current. So what is flowing? It's a charge that is flowing per unit time. So no doubt, the concepts that you used with the water flow before works. Okay. And you can imagine that the current flow to be exactly just like water flow. Same thing, except It's not the volume of the water that you are looking at now, is the charge that you want per unit time. So the unit of this one is a coulomb per second. And we have a special name for this one is the ampere. So I think you guys familiar with this because you use like a smartphone adapters already, right? So when you buy one, you have to know what is the wattage of the adapter. And before that, actually, you can just look at how much currents that is flowing through your adapter as well. So it depends on what kind of spec you want to read. So that current flow is the amount of charge that can be transferred per second. Yeah, that's good. So there's a question. Nah, it's an oscillation of electromagnetism. What is that? All right. So what you have over here is just well, we'll talk about that later. Okay. So what we have over here is the flow of the positive charge will determine the direction of the current flow. All right. So even though in reality is the electron that's trying to go backward, right? But we can imagine everything to be positive. It's kind of easy. Okay. All right. So with that in mind, usually the way that the electric flow is just like water's flow. Usually you cannot just have like a free flow. It's impossible for you to flow without any resistance. Just like in the water flow in a pipe, you must have some sort of like a resistance to the flow. Same thing with the currents. So the resistance to the flow in the topic of the current, we call the resistance. Okay, which is going to be the same name as the fluid flow, I think. Yeah, but over there they call it a fluid resistance or something. All right, but it's a resistance anyway. And the unit of the resistance, we have the name is ohm. However, to be able to drive the current flow, you need a potential difference again. So this one in your head, it's exactly the same as a delta V. So in the fluid analogy, this one is going to be the same as the delta P, the pressure difference, right? When you want to drive a water to flow in a pipe, you need some difference in pressure. So you'll be able to have some force to push the water to flow. Same idea. So that's why back in the day, they might have a name for this one to be like electromotive force. There is the word force in it because it seems like it's something that's pushing the current to flow. Okay. All right. So with that in mind, it turns out the flow of the current depends on how big is your potential difference. And of course, if you have resistance, it will be inversely proportional to this. So with this in mind, then you can say, okay, the current flow is just depends on the delta V and the R. So that's why you get an Ohm's law, I equal to V over R. And that's it. You're done. Okay. So this equation looks exactly just like what you had before back in the day of the fluid dynamics, except, all right, every term is just being electric now. Okay. All right. Now, the way that I want you to think though is this. So every time that you have resistor, so to be able to mention about the resistor in the circuits every time, because it sort of like exhibits the resistance to it. So you try to put some sign to look like a zigzag over here to make it like, okay, having a tough time going through. So this symbol will represent a resistor with a resistant R. Then let's say that you have a way that you can drive the current to flow through this. So this as in the indication that there must be a potential difference across this. Does that make sense to you? To me, that is pretty much everything that we need for the circuits analysis. If you have a resistor that doesn't have anything flowing through, the current is zero, let's say. So there must not be any potential difference across either. Does that make sense to you? Okay. So to me, all I think it's just like if you need a flow and if that flow can happen through any resistance, there must be something driving that flow. And that thing that is driving is just the potential difference. And that's it. So that's why Ohm's law is sort of like very easy to use and it's important in circuits analysis because that allow you to be able to calculate potential, the currents, and everything around any resistor in the circuits. Okay? All right. And that is one perspective that I think we can understand is very easily now. That see, I mean, I just want to show you that everything that we learned over here just came from understanding of the basic concepts about potential, about the energy, about simple charge movement and everything. Think about this. If I go back to the concept of the power, energy per unit time. So, okay, well, Ajahn, it's just the electric energy per unit time that you need to put in. However, we already understood that we defined the potential energy to be just a product between the potential, without the word energy, multiplied by the charge that's flowing through. See, that's kind of useful. And then you look at this pair over here, just leave that delta V alone. Well, oh, Ajahn, that is the amount of charge per unit time. Okay, and that is the definition of the current. And this is a reason why you are able to calculate the wattage of any device that you use. Like you have like a the adapter charger, for example. You can just look at how many volts that is supplying and what kind of current that is actually can supply. And then you take those products and then you know that what is the size of your adapter, how many watts of your adapter, something like that. Okay, so I think you probably have used this a couple of times when you try to buy an adapter, that now you have to understand like which one is like a slow charge, super fast charge, ultra fast charge, or whatever. It depends on your wattage, right? If you buy just like a small stuff, then you probably don't get a lot of it. Yeah. Yeah, there is a relationship about this one. However, I think when they rate your adapter, they rate the output. And of course, they have to convert between AC to DC first because your phone or your laptop use a direct current. That's what we are looking at this point. So that adapter over there will convert the alternating currents from the household current into a direct current. Yeah, even though we're not spending time about AC here in this course, but that's what it is. And then the outputs of that one, that is the numbers that show up on that adapter. I think they focus on what can this adapter delivers to your device. So the numbers over there is already is a specification for a DC output. Yeah. All right, but that's a good question though. Yeah, it has. Yeah, it needs more detail, right? If you really want to dig into it. All right. And another thing about this one is, so that means from now on, when you have a product between the current and the voltage, you always be able to calculate the power. So that's why you probably have seen these equations somewhere, somehow back in the day of like high school science. The power is I times V. Yeah, I can drop the delta anytime I like. And if you combine this with this expression over here, and this one is the Ohm's law. I think it's a famous one already. Yeah. So you can manipulate this into whatever you like. For example, if you don't like the voltage here in the equation, you can use V equal to IR. So you can turn this equation into I square R. Or if you say I don't like the I can use I to be V over R, and then you can get to the last expression to be V square over R. So this is sort of like convenience for you to be able to calculate the power usage or the power supply or the power provider anytime that you have two of the informations, current, voltage, or resistance. Okay, good. All right, so this is nice. So this is something that I think when you do shopping at the store, you want to buy a light bulb now, you want to know how bright or how many wattage that this thing is using your electricity. So for example, over here, you have a light bulb that marked with the 2 watts that using 1.5 volts. So now you should be able to calculate the resistance inside the bulb, for example. Yeah. So this is good. You know the P, you get the V, you want to know the R. So P is just V squared over R. And then you should be able to calculate the resistance in there, something like that. Even though you're probably asking, but why? Do I have to care about the resistance? Something like that. Okay. R. Oh, I erased the wrong one, guys. Sorry. No, you probably don't need to know, but just like you know how to calculate it. All right. So maybe sometimes you want to know. because you want to know like, hey, how much your electric bill is going to be, something like that. Okay, cool. All right then. So that's the topics about the power in the resistors. All right. However, now in reality, I want to just sort of bring you back to the circuit analysis. So what you have over here is the way that you can think about the resistor is this. If you have a resistor that we have the zigzag symbol for it, and we know that you can drive the current through. So that means there is a potential difference across this one. Okay, everyone sort of agree with me with this. When you have a different of the potential, it means current flow from high to low. So you know right away that the left side is high in potential and the right side is low in the potential, right? But then because we want everything to go through the whole thing and come back again, because you want to keep supplying to this. So that means once you're already on the right side, it has a low potential, but you want it to go back and then, do the flowing again. So you must be able to pump, or you want to lift that energy of that charge that already low on the right side to get high again. And that is the duty of your battery. So when you have a battery, one is negative, one is positive. So the ability of this one is just once the charge that has a low potential hit this one sort of like pump it up into a higher potential again, so it can flow and have an ability to get through that resistance one more time. Does that make sense? All right, so that's why this is a shape of a very simple circuit. It's composed of the portion of this one that generate the potential difference. Sometimes they call electromotive force because this is like the force that push the charge in the currents, in the circuits. And this one, there's an R to it, and there's a current flow. Okay, so that's why this ends up to be the simplest circuits possible. One source of the electric potential difference, which is a battery. That's a common example of it. Of this one, the resistor. The resistor can be anything that used energy. It could be like a light bulb. It could be like a electric appliances. It could be like microwave, TV, whatever things that use. You can represent everything as an R, and then you have a current flow in it. Okay, does that sound good?
Okay.
I hope this is good enough for you to sort of like revise what we have been doing back in the day of the Ohm's law. That's what we have. Cool. All right, now this is what I have been talking so far, circuits. All right, so I hope you understand this slide, and it's about the simplest electric circuit possible. Okay, in terms of the notation though, even though in the textbook, some textbook, they use positive and negative shape like this, but this one can be equally represented as like a non-equal straight line like this. The longer one represent a positive side of the battery, the shorter one represent a negative side of the battery. Okay, but for the resistor, it's pretty universal. They use like a zigzag symbol to represent a resistor. All right, and label R to give you the magnitude of the resistance of that resistor. Okay, this is the actual stuff that could happen. The battery could be a real car battery, for example. And this resistor is more like an electric circuit resistor. It looks nice and cool. All right. But you can replace this with like a light bulb. Textbook love this. Or it could be like a, TV, still have an antenna on there. All right, here we go. So with that in mind, now if you have more than one resistor in the circuit, so you say, Dan, that's no big deal. If you have more than one resistor, each resistor will take some energy out of your initial supply of energy. Or if you want to talk about just the potential is the same as the energy, right? But it's just per unit charge. So if you want to talk in terms of the potential, so it means you come up with here super high potential because you just came out from the positive ends of the battery. And then you just keep traveling, and then you hit the resistor, first one. And because you want to be able to push through, so that means there must be a potential difference across this one. Let me name it V sub 1. How can you calculate V sub 1? it's going to be the current flow times I1. See, simple Ohm's rule. And then you keep going, and then you go another one of this, you have another resistor R2, because you can still go through with it because the current still flow. So you have the potential difference of IR2. But then you come in, you come, now you hit the negative ends of the battery. The battery will lift the energy up and then send it through the whole circuit one more time. Okay. So by the whole thing, we understood the concepts of the potential energy. Everything come back to the original position. There must be no potential energy change. You guys with me? Yeah. And if you sort of agree with this, we are almost done. So let me think of this lower left corner to be my initial point. I am going along this path over here, seeing the first potential change V1, keep walking. I see another potential change V2, keep walking, and then I say, oh, there is an increase in potential E. And now I come back to the original position. The whole changes that happen along the way must sum up to 0. You guys with me now? Go back to our, beloved analogy of the gravity. You start a mass here on the floor, you bring it up, you increase its energy, and then you bring it back down, you reduce its energy, and then back to 0 again. So the change that's happening along the path, whatever, once it comes back to the original location, there must be no change. And that is the Kashaf Rule that we are about to study. See, it's apply our known understanding of the property of energy. We knew that. So what we have over here is, all right, you coming here, there is a V1, you drop in energy, right? You drop the potential. The potential change is negative V1. Okay, let me write it over here so you won't get confused. So the delta V along the path is going to be negative V1 once you're going through R1. And then you're going to R2, you have another drop in potential because, okay, it's getting lower. But then you get pumped up by the battery of E. But this summation must go to 0.
Okay.
And that's why you get this equation. So you like this go back to Ohm's law back in the day, why the potential difference from the battery must be equal to the sum of the potential in the circuits because of this. Okay, sounds like a good plan. So I hope by showing you this, you sort of see the relationship between what we are doing in the circuits and the understanding of energy. The concept of energy is path independence. That's a nice thing about it. Cool. All right, and that leads you to a couple of things that you can do with the circuits. If you have more than 2, for example, like this one, you have 3. It doesn't matter. E must be equal to V1, V2, and Vt. But then each V can be calculated by the current multiplied by the resistance, current multiplied by the resistance, current multiplied by the resistance. And that's, I can pull a common factor I out. And then you see this? Dan, it's just a summation of all those resistance. That's why they name this a combined resistance or equivalent resistance. It's just going to be the sum. And then you probably go back in the middle school science saying that these 3 resistors are being connected in a serial connection. And then what you get at the end is you can find the equivalent resistance by just sum all those resistance together. Woohoo! All right. But everything seems to come from just analysis of the potential, it looks like. But then there is another way of connecting these two. But Ajahn, wait a second. If you are not trying to do everything in serial, but you want to have a branch, see, look at this, A. You're breaking into 2 paths. Now, the stuff that we did before which doesn't seem to work now. Wait, Ajahn. You're splitting, so the path have like 2 paths. Then you should be able to choose which path to go, but what is going on here? Don't worry, the concept stays the same. Okay, the potential due to the battery must still be the same as the potential across A and B. Why not? That must be the same. However, whenever you have a split, you can pay attention to the current flow now. Because, I mean, the potential across must be A and B. But then the thing is, the current flow on each branch of these lines are not going to be exactly the same anymore. Why? Because the current flow is just like water flow. When you have a branch, when you have a conjunction, you have the split, water has to split too. I mean, you cannot just, have more water or, some water can disappear. No. So this means if you have an incoming current and then now you split into two tubes, for example, or pipes, then some of them will go to one, some of them will go to two, but the sum of these two will stay the same. So you have this conservation of charge. We understood that because charge is there, is real. You cannot just avoid it. So the currents in must be equal to currents out. And then you have to go through this sort of like Ohm's law again for individual terms of this one. For example, you look at this one, Ajahn, I equal to, from Ohm's law, E over R. And because potential across A and B is going to be the same as the potential across battery, the E over there. So I can say that I1 is just going to be E over R1. Why not? The current flow over here is I1. Sorry, let me use black color here. Okay, here we go. I1. See, every time you have a current flow through the resistor, you can use Ohm's law anytime. So the current is just I1 equal to E over R1. I2 is going to be E over R2. See, down there, I2. I just write one more time just to emphasize where I am looking at. Okay, with that, you have a common factor of E right there. I can pull E out. And can you see this? I think you can guess. So I can name this 1 over R1 plus 1 over R2 to be 1 over R equivalent. And then I can define the equivalent resistance in this type of connections. This one, we call it connections that is in parallel. So this is a resistor in parallel connection. Cool? Well, it's a comment there, connect resistors, save diodes. What does it mean? Oh, but that's kind of true though, right? Don't want to blow diodes away. All right. Okay, so with that, this revise one more time. If maybe you learn it from high school science or the stuff or physics, that if you have a parallel connection, you do this. You do the reverse sum, reciprocal summation, right? 1 over sum. All right. But anyway, with those in mind, you should be able to sort of like, okay, I want to combine this into a final single R. There you go. What can we do? So all you need to do is just apply those stuff. I'll show you this one and you'll see how it's done. But just for fun, because this is the kind of thing that I'm not going to ask you in the exam because you'll probably, get bored with this. Like I won't give you like a unicorn shape of the resistors and then find the equivalent resistance. No, I'm not going to do that. But anyway, this will showcase how it's used one more time. So the way that you can do this first by looking at some part that you can pretty much sort of go find the equivalent resistance easily. Like here, between these two green dots, those two are connected in parallel. So that means the first step that I can do is gonna look like this. It's gonna look like 4 ohms is still there. I'm gonna reduce this into a 1, and I got a 9 is still there. Does that make sense? Okay, and the way that I can fill up this space over here, let me name this sigma R for now. Let's use like sigma R1 then, because I'm gonna reserve sigma R for the final result. So the way that you can figure out this sigma R1 is you just look at these two and you can say 1 over sigma R1 is gonna be 1 over 7 plus 1 over 10. That's it. Okay, remember this one vaguely, I hope. And from here, you can say sigma R1 is just going to be 70 over 17. Nice. All right. Once you have that, I can combine this whole thing into a final sigma R. And I'm just saying that the sigma R now is going to be 4 plus 70 over 17. The numbers look so bad. 9. And that's it. You done. Okay, cool.
Okay.
And once you have this, part B of this question is going to be very simple. If the potential difference is 43 being applied between point A and point B, so you just apply the voltage across delta V. What will be the current going through the resistor? First thing first, you will be able to figure out the whole current flow. Let me put big I over there. And the big I over here is going to be simply Ohm's law. So that is done. So you don't have any problem finding out the current's flow. But where does this current actually flowing? Go back to the first figure over here. The current will flow in here, going through 4 ohms, right? So that's the first answer. Current through 4 ohm is I. And then you keep going. Now you see a junction. Now you have to go a little bit further going through like, hey, I'm going to have to split between the two. Okay. But then how much that I want to split, I have to figure out. How can you figure out? Here we go. Because you know that the incoming current is I, let me name the upper to be I1, lower to be I2, because they have to split, right? So one thing that you know for sure is I, the capital I must be equal to I1 plus I2. Okay.
Okay.
This is nice. But then you know further that it turns out what you need is you need to know that there is the current flowing through 7 ohms. So the voltage across, let me call the upper path over here, V equal to I times R. So it's going to be I1 times 7. You guys with me? But then if you look at the bottom path, the delta V on the bottom is going to be I2 times 10. You guys with me? But then, Ajahn, wait a second. These two are exactly at the same initial point and the final point of the junction. So these two potential must be exactly the same. Delta V in the upper line or the upper path must be the same thing as delta V from the bottom path. And now you get two equations, two unknowns for you to solve for I1 and I2. Okay, it looks tedious a little bit, but it's doable. Given that you sort of like apply all those stuff that you have already learned and then just slowly, sip through this one by one. And once they combine back, of course, the current that coming out is going to be I again. So the current that going through 9 ohm is going to be the capital I. And you are done. So why do I do this? Yeah, even though it's a long sort of like review process, but I think you are ready to get to the Kashaf Rule, the final step that I want to talk about in this course. I don't know. This is like a good review, or I don't know. Is this your first time seeing this or not? But anyway, for those of you that haven't done this kind of thing, I hope this, give you some initial starting point. All right. I think you might still have to dig a little bit deeper. I mean, practicing a little bit, but I hope at least it seems like if you catch the detail of my analysis here, there are only 2 things that you need. And it turns out that 2 things are the 2 that it's going to sorry, it are the 2 things that's about to show up in the Kashaf's rule. Seriously. All right. So this one, practice and see if you can do it. I think I have some in the homework in about this range. You should be able to, I mean, it's not going to be it's not going to be like more crazy than this one. I think this is about right. I mean, about to be too much already. All right. I'm not want to sort of like focus too much on this, because what I want to focus on is this. It turns out the Kashaf's rule is just the 2 things that we just did. What did we do? Junction, guys. Every time that you see a junction, the current in must be equal to current out. And that is a junction rule. You already get half done. And the other one isบอกอาจารย์ every time we went through a loop all of the changes of the potential must sum up to zero, right? And that is another 50% that's called loop rule. Combining these two rules, you get Kashaf rule for. Okay. All right, I'm going to show you how easy it is to use this one to solve this kind of circuits. This is my finale here. This is the last stuff that I want to talk about. All right, so before we get to that, I'm going to show you right away, and let's see if you agree with me or not. All right, just based on what we just learned, you all now know how to do this. First thing first, look at this circuit in a little bit. And then imagine that if you don't have any Kashaf rule, how can you solve these problems? The problem is simple. Find all the current flow in the circuit, I1, I2, I3. That's it. That's the question of this problem. Figure out all the current through all of these parts of the circuits. When you look at this one, about that serial connections, that's parallel connection doesn't help. It does nothing because it's all over the place. And here comes how it's done for the Kashaf rule, guys. First thing first, you might not even have the current defined. Oh, why is not white? White. I want white. Okay, white. Okay. What happened? Sorry. White. I want color white. That's weird. How come it's kind of transparent? No, okay. Sorry, guys. It's not white. Okay, just kind of white. No, okay, all right. My bad. I think I got it at the wrong place. Sorry. Okay, even though at first you might not even see anything at all, nothing. That is a kind of circuit. Of course, in general, the circuit will give you, of course, there will be no arrows, there's no, labels or anything. This is it. This is like a plain circuit. Opacity, maybe. Thank you. Yeah, I think I picked the white for the highlighter. So it's like highlighting nothing. Sorry, my bad. That's a weird highlighting. Okay, so here. So you have a circuit like this. You have to figure out the current that is flowing through all pieces, all of the area of this circuit. How can you do it? Now, this is a process of doing, okay? How many wires can you see that is like a straight wire without any break, without any split? What you are seeing over here, you're gonna see 3 of those wires. The one on the left, see that? It's a single connected line without any splitting. The one in the middle, yeah, and the one on the right. So these are the 3 wire without any splits. Cool. The reason I want to identify this wire because anytime that you don't have any splits, the current that is flowing in this wire will stay fixed. Because when there is no split, then the amount of current flow will stay fixed, stay the same. So by having that, I can identify that, okay, my yellow line will have current flow I1. Let me name it I1. But then, Ajan, which direction? I don't care because I don't know. So you can imagine like, okay, let me put it like up direction. Let me name this I1. That's my point, my choice. Sorry, that's my choice. Okay, I picked this randomly. I don't have any clue. And now I move on to the second one. The middle line, the blue line is a single wire. I would say they should have another current flow. Let me name it I2. And then there's a third one here. I can say I still like going up. So I will call it I3. All right, that's done, first step. Now the second step, I'm going to use my, here we go. Let me change back to black. Start with loop rule. Oh, I'm sorry, junction rule first. Junction rule. Let's make it clean. Junction rule. And the junction rule is saying that wherever you see a junction, the current flow in must be equal to current flowing out. How many junctions can you see here? Well, of course, down there are only two. It's either A or it's either B. So pick one. Let's look at the A. How many current is flowing in? Well, then is I1 is in, I2 is also in, I3 is also in. So there are I1, I2, I3 that is in. And then plus, and then equal to, what about the currents flowing out? Nothing. That's fine, because you assume that everything is just into the junction A, and that is your equation number one. All right. What's stopping me from simulating this to find? Hey, it's a written exam, guys. So you're supposed to write me the reason for it, not how. Like you're not supposed to like, okay, after putting these numbers into a simulator, this is the final. Of course, you can do that. I mean, you can do that, but you cannot do that for the final exam paper though. Okay, number two. Now that's done for the junction rule. So I hope you understand what this rule is. That's simple. Just say, figure out that at any junction, currents flowing in must be equal to currents flowing out. You get the first equation done. But the thing is, just the first equation alone, you see that now you have three unknowns waiting for you to solve. So you need two more equations. And those two more equations comes from the other rule that you still have left. It's called loop rule. But if you look at the loop rule, it's a simple rule that we already did. At any loop, the potential difference across that loop must sum up to zero, just like what we did back here, back here. See that? Yeah. So when you sort of like, okay, I'm starting from lower left corner, and then you keep going along the path, and then up there is a V1, there's a V2 arm, and then you come down here, and then up there's a battery there. Come back to the original position. You say the sum of those delta V must go to zero. So I can put the summation sign over there, because along the way you might have different portion of the circuits that change the potential. So it's just, okay, collecting those terms. Go for it, man. Well done. Which closed loop you want? Any closed loop, guys. Pick one that is closed. So what I'm going to try to do along with you guys is this. So let me name this corner M, N, O, P. Yeah. All right. So we can sort of like communicate better. Okay. Let me move I3 out of the way a bit. Okay. That's I3. Okay. All right. So let's pick a loop that is closed in any direction you like. So let me show you one. I'm going to pick M, A, and then now I turn down B, turn P, back to M. See, this is my loop. So the loop that I'm talking about here is this loop right here. Here. That's my loop. Okay, so it's a left-hand loop over here that I'm looking at. So what I'm going to do is this. I am going to just analyze along this loop. And along the way that I'm analyzing, I'm just going to collect the potential difference. You guys with me? And that's kind of simple now. So let's give it a shot. So walk along with me, guys. So I'm going to start from the upper left corner. Here we go. That's my endpoint here. I'm just going to go. Now I'm seeing R1, but the R1 has the I1 current flowing through. You guys with me? Okay, so that means the current is flowing from high to low. So now I'm going in the negative I1 R1 direction. That's pretty good. That's potential difference is just I times R. So that's it. So going through R1, my potential changes negative I1 R1. Keep walking, guys. Now I hit point A, I turn. Now I see R2. R2 have an I2 going, but as you can see, the I2 is going in the opposite direction as we analyzing, right? So is it indicator saying that we are seeing the current is actually flowing backward? So that means we are going toward the higher potential. So that means going through the R2, the potential change that happening is going to be up. It's increased R2, I2. You guys with me? All right, keep going. Keep walking. Okay, let me zoom in a bit so you see a little bit better. There. Now I hit a battery, but now I'm going from positive ends of the battery to the negative end of the battery. So it means I'm going downhill. But woohoo. So I'm going negative E over there, which is E2. All right, nice. Keep walking. Oh, what is going on here? Now I hit another R1 down here. But as you can see, the R1 having the current flowing through it, which is, okay, just mark the direction over your eyes up one here. So you are walking in the same direction as the current. So that means the current is flow from high to low. So over there, your current flow is going to be another lower in potential, I1, R1 down there. Okay, keep going, guys. I don't know if you have fun or not, but that's what it is. Keep going. Keep going, keep going. Now I see another battery, E1, but now I'm going from negative polarity of this one, go to a positive one. So it's me, I'm going up, right? I'm going up, increase the potential. So I'm going to have positive E1. Now I'm walking back to the original point M. These collections of the potential change along my way must sum up to 0, and that's it.
Okay.
Let me call this equation number 2. Isn't that cool? So even though, I mean, it sounds long because I have to, talking and what is going on, but let's do one more loop because that's what I need. We need 3 equations for 3 unknowns. So if I can figure out one more loop, I'm ready to solve for I1, I2, I3, and then I'm done solving this problems. So go for it, guys. Let's do another loop. Which loop you want to try? Let's go counterclockwise, shall we? So let's start with M. I'm going to P, going through B, all the way to O. So now I'm going to do outer loop over here and back here. So it's going to be N, A, and M again. So that's an outer loop in the counterclockwise direction. And let's see what will give us. Let's start from the upper left corner. Keep walking down, guys. So everyone, okay, I think I have to write now. I cannot use highlight anymore. It's going to get crazy. Okay, I'm starting from up here. Okay, walking. Now I hit the positive ends of this battery. I'm going from positive to negative. So it's downhill, negative E1. Very good. Oh, I see R1 again. But now the current is actually go against me. So when it's go against me, it means the way that I'm going is going to be at the higher level. So it's going to be positive I1, R1. Make sense? Keep going. So now I'm going through R1, keep walking. Nothing is going on. Now I'm arriving at point O. Now I see R1 over here. But then at the R1, I have the current I3 going through. I am moving sort of like analyzing upward, and the current is flowing in the same direction. So it means I'm going in the direction of lower potential. So at this point, I'm going to get a lower potential negative sign, I3R1. With me? Okay, keep going. I hit the negative ends of the battery. So I'm about to go to the positive end of the battery. So I'm going uphill because the battery will pump me up. So it's going to pump up with the potential difference of E2 right there. Keep going. Now I'm at the upper right corner and turn. I see another one here is another R1 with the current I3 in the same direction as my analysis. So I'm going in the downhill direction, right? Because current flow from high to low. Negative I3 R1. Keep going, guys. Now I'm at A, nothing, nothing. Now I hit another R1 on the top, but then the current I1 is going through me, against me. So I'm going from low to high, right? Because I'm going against. So what I'm saying over here is going to get positive I1 R1. Done with that. Back to M. These changes in potential difference across each devices along the way must sum up to 0. That's my third equation. 3 equations, 3 unknowns, plug in the number, solve it, and you are done.
Okay.
That's Kashaf Rule, guys, in action right here. I think if you have a chance to practice, like maybe just only a couple or a few exercises, I think you're done. You're in good shape because it's so easy to use. It's a linear equation. You only rely on Ohm's law, and all you have to do is just start with the junction rule, set up the whole currents and everything, apply the junction rule, you get the first equation. Then you move on to a loop. Analyze the loop by collecting all the delta V along the way. The sum of those delta V must be equal to 0. But then you'd say, okay, that's not enough because in general, if you have that many unknowns, you need that many equations to solve. So it's just no problem, I'll figure out another loop and then you get another equation. Once you have enough equations for your unknowns, solve them. You have a system of equations to solve, done. Okay, and it's guaranteed one of these I that you have as a solution of this system of equation is going to be a negative number. You know why? Of course, because I mean, you intentionally have the current flow in. It's impossible, right? So there must be some is going out somehow. So don't worry, the mathematics will take care of itself. All this system of equation will have the final solution. So if some of these numbers turns out to be a negative current, that means your assumption of the currents that is flowing is going to be just opposite direction. You see what I'm saying? For example, if I1 is negative number, it means the current is not flowing upward as you assumed, it's flowing downward. That's all. Okay?
Okay.
That's kind of nice. So I hope you guys see this to be all right and doable. Okay, so I think I have a couple of this exercise for you to try, but I will show you one more. So just to make sure that you know how to sort of set up the system of equation. And once you know how to set this up, you guys try a couple more and then I think you're good to go. All right, shall we? So this is going to be our last exercise of the course. So I was like, okay, it's kind of sad, but that's it. All right, and the topics about the RC circuit, I think we don't have time. And as I said, we're not trying to push anything too much. So don't worry about it. We're just going to end this course with the Kashaf Rule. All right, so let's do one more, our final exercise of the course right here, guys. Same type of question. Every time that you cannot use the serial connections, parallel connections, doing equivalent resistance calculation, just try Kashaf's rule and it seemed to help. All right, especially if the circuits look like a loop already. It seems to be a good one. So let me sort of define all the position here. M, N, O, P. So this one look really just like what we did before. Okay, so what do you see in terms of the path that you can identify as a single line without any break, any split? So you say once again, the left side of this one, the medium, the middle one, and the one on the right. It's pretty good, just like before. So what you have to do next is just define the current that is flowing in each wire. So let's change the mood a little bit. So I'm going to have this one flowing down. Let me call this I1. This one flowing down. Let's call I2. And let me do this up for I3. Nah, no big deal. Wait. Is this the same circuit as this one? Oh, no. They look the same. All right. And that's it. All right. You start with the junction rule first. So number one, junction rule. Okay. Which junction you like? You can say, well, done A, just like before. Okay. You can use B. You get the same type of equation anyway. So let's try B. Let's look at B. See, I1 is flowing in, I2 is in, I3 is out. So you have I1 is in, I2 is in must be equal to out. That is your first equation. That's it. Three equation, three no. Next, let's apply loop rule. Very good. Okay, now pick a loop. So let's try the outer loops, shall we? Why not? Let's do, I can do clockwise. Let's do clockwise. M, A, N, O, B, P, M. So that's the outer loop right there. Ooh, right here. Okay, and then the rest, just try to use the loop rule, collect the delta V along the way. All right, guys, start walking from the M, see the I1. The current I1 is flowing against you, so you're going uphill. So it's gonna be positive I1 R1. With me, guys? Keep walking, keep walking. I see another R1 there with the I3 going against me. So it's mean I'm going uphill. I'm going through a higher potential. Keep going. I'm at end turn. Hit the battery on the positive ends of this one. So it means I'm going from positive to the negative. So I'm rolling downhill. So it's going to be negative E3. Keep going. Oh, I see another R1, but then the current I3 is going against me. So I'm going walking uphill. So it's going to be positive I3 R1. Cool. Keep going. Nothing, 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 nothing until I hit R1 on the left, on the red path over here. And then once again, the I1 is going against me. So it's me, I'm going uphill again. Nice. Nothing happens. Turn. Hitting the negative ends of the battery. So I'm going from negative to positive. I'm lifting myself up, increasing my potential a bit, E1. Nice. Back to M. I'm done. These sum to zero. My second equation. Woohoo! Well, and that's not enough because you have three unknowns. Just pick one more loop, any loop. So let's try the right loop, shall we? So let's do that right loop over here. So let me sort of try it here. So look at the loop A, N, O, B, A. You can do counterclockwise too if you like. I mean, it doesn't matter. Okay? It's just like multiplying negative to the whole equations. That's all. All right. So start from A, see R1, I3 going against me. So you are going uphill, I3, R1. Keep walking. Nothing happened. Oh, meet the positive ends of the battery. You're going rolling down. So you're going negative E3. Actually, just like what you already saw back there. You have another R1 with the I3 going against you. So you're going uphill. It look like this, right? These three terms, just the same thing. You're just walking in the same path. So there's no change on that. So just keep walking, nothing changes. Up until now, you turn at B, you hit the negative end of the battery, but you're going from negative to a positive end. So you lift yourself up, increase in potential by A2. Very good. Keep going. And then now you see another R2, but then your R2 having the I2 going against you. So it means you're going uphill again. So it means you're increasing the delta V by I2 R2. Now you arrive back at A. This sum to zero, third equation. All right, plug in all the numbers, solving the system of equations. You are done.
Okay.
Okay, not too bad, guys. All right, so I hope this is going to be useful later because actually this simple trick works everywhere. Works everywhere, no matter how big, how small, or you just care only a portion of the circuits or whatever. It's Ohm's law, so it works pretty much everywhere. But this one is kind of like nice for a multi-loop circuits. Yeah, and that's easy to use. All right, guys, I think this is a good place to stop. And anything, I'm gonna close down, close down. Gonna shut down this course now, right here. All right, I hope you learned something and have a little bit of fun with physics. And then, well, because our final is going to be um, open book take home exam, so you don't have to worry too much about preparing, memorizing anything. Yeah, sounds good. So thank you very much. And all right, I'll see you. Don't forget to try the homework. I think I will set up like a homework, final homework submission a little bit, so you have like extra points for you to collect. But the main points will come from the exam. All right, and the second exam score will be. I mean, I will directly connect. Sort of put the score in the Google Classroom, so you can check that out. Exam number one should be coming out soon. Working on it. All right, guys. Okay, thank you so much, and then see you in the final on December 12th. Is that right? Yes, on Sunday. Okay, but then we have a special session on 11th. If you guys want to have any Q&A or anything, I'll set up a session for that. All right, bye-bye, guys. Take care. See you soon.